Welcome. Today, we're breaking down the key differences between DC, AC, and EC motors, how they work, how they're controlled, and where each one excels. This is another lesson we're doing with our friend of CircuitBread, Orion fans, whom we also worked with to create the lesson about brushed and brushless motors. These types of motors are the most common options not only for fans, but also for any project that needs rotational motion. To clarify up front, DC, AC, and EC stand for direct current, alternating current, and electronically commutated motors. We'll start with DC motors, which if you've already seen our other video, will just be a review. What we have here is a brushless DC motor. It operates on direct current, just like you'd get from a battery, a DC power supply, or even directly from something like a solar panel. A brushless motor has an electromagnetic stator that is stationary, and the direct current flows through the wires of this stator to create a magnetic field. There is a permanent magnet rotor that, for this fan, is mounted inside the fan blade. A simple controller, which is what this printed circuit board is for, detects or estimates the rotor position. Based on the position, the controller switches the current direction through the stator, which also reverses the magnetic field it generates. It's this continually reversing magnetic field that provides a force on the rotor spinning it. While the motor itself has no brushes or mechanical commutator, it still requires an electronic speed controller, or ESC, to control speed and direction. Brushless and brushed DC motors are definitely different, and you should go check out that other lesson that shows the difference between them. But in general, DC motors are compact, easy to control, and great for applications that need variable speed or precise motion, like drones, robots, and electric bikes. AC motors are interesting because with DC motors, the big challenge is getting the current to switch direction. Not a problem with AC motors. With the alternating current, the current changes direction cyclically, and the motor is usually what we call an induction motor. No wires or direct connections are needed to get current into the rotor. It just happens through the changing magnetic field, making it very durable. Actually, this fan was extremely durable in general. I had a heck of a time taking it apart, as you can probably tell. You'll see here in what remains of the shaft connected to the blades that there are conductive bars running vertically up the shaft. As the AC power goes through these stator windings in the base, it creates a rotating magnetic field. This magnetic field passes through the bars of the rotor. This changing magnetic field induces a current in the rotor, which then creates its own magnetic field. The interaction between the stators and the rotor's magnetic fields produces torque and causes the rotor to spin. Basically, the rotor is following the rotating magnetic field of the stator, but never quite catches up. As I mentioned, AC fans are simple and durable, making them a rugged solution. They can also be connected directly to mains power without the need for rectifiers or external controllers. However, if you want to change the fan speed, things are a bit more complicated. For smaller motors like this, you can use a triac or variac to change the duty cycle or voltage of the AC power, while for large three-phase AC motors, you could use a variable frequency drive. Also, due to the nature of the setup, AC fans are typically heavier for the same power rating as their DC counterparts, and they also have lower starting torque. Three-phase AC motors that you find in industrial settings actually mitigate some of these drawbacks and are quite efficient and powerful. Finally, there are EC, or electronically commutated motors. These are interesting because they are essentially a brushless DC motor with more controls around them and the ability to provide them with AC power instead of DC power. So thinking back on the brushless DC motors we just discussed, all of the physics principles of how they work are still there. But now, the EC motor can accept AC power, internally rectify it, and use the resulting DC to drive the motor, meaning these can be a drop-in replacement for AC motors. For control, it also has an internal electronic controller which controls speed, monitors and regulates performance, heat, current draw, external signals, and any other fan properties that are part of the design. I've heard it said that you can compare a brushless DC motor to an engine, while an EC motor is like an engine prepackaged with a smart transmission and a control computer. As such, an EC motor is very efficient, requires very little maintenance, and is highly controllable. On the flip side, their upfront cost is higher because of their higher complexity. And those are the three most common types of motors. DC and AC motors work on very different principles, and they have their unique strengths and weaknesses. You can think of EC motors as the best of both worlds, the control and efficiency of a brushless DC motor with the plug-and-play convenience of an AC motor, though at an additional expense. I'd like to thank Orion fans for helping us develop this lesson and providing me with the 3 different types of fans that I could destroy to show you their innards. You can support us here at CircuitBread by learning more about Orion fans either at their friend page or visiting their website. If you found this video interesting or helpful, give it a like, subscribe to our channel, and we will catch you in the next one. Take care. We hope that you enjoyed this tutorial. Did you know that CircuitBread.com has other useful engineering content? In addition to many other features, we have study guides that cover a wide variety of engineering topics at a high level, with equations and diagrams to make it easy to quickly review and reference. Go check them out.